So good morning, everybody. I apologize not being in person in San Diego. I would like to thank the organizer to invite me to present you the results we obtained on an Android protoplanetary disk with the near-infrared interferometric instrument Gravity that is installed at the VLTI of ESO in Chile. And this talk is on behalf of the Gravity collaboration. So a few words of context. The confirmed planetary systems exhibit a wide diversity in orbit, in mass, in nature, in architecture, in atmosphere, with super Jupiters separated by tens to hundreds of AU to a very compact system separated by just a few AU or less. And the Kepler population that is depicted on the left, that is represented by a symbol located at the distance of the host star, show that many systems are in the orbit of the Earth in blue, but even within the orbit of Mercury here. And so to understand the diversity, this diversity and which processes determine the final outcome of planetary system, we need to probe such kind of scales. And again, to set the scale, I have superimposed here the sketch of the magnetospheric accretion scenario when the inner disk is truncated by the magnetic field of the star, was a magnetic field line as they are depicted here in red, and where the matter is funneled onto the star. So we need to probe such kind of scale to understand which initial condition would favor such close-in planets. So to understand this diversity, we need to explore the birthplace of these planets that are the protoplanetary disk, that are the material reservoir from which matter is accreted onto the star and from which planets are built. And the accretion of disk material onto the stellar surface directly impacts the star's properties and its early evolution. And it also produces radiation that illuminates the circumstellar disk and the proto-atmosphere of nascent planets, thus drastically affecting their physical and chemical evolution. So star formation, planet formation, and disk evolution influence each other. And if these interactions are brief and last a few billion years, they set the stellar and the protoplanetary properties that persist for billions of years. And thus, if we would like to understand the formation process, we really need to observe the structures and the evolution of protoplanetary disk while planet formation is happening. So you all know these beautiful images of the outer disk with ALMA or with sphere, but what we would like to do is really to zoom in to look behind the coronagraph of the sphere instrument, for instance, to probe the inner rim of the dusty disk, where dust traps or vortices can occur, where micron-sized dust grains grow to pebbles and larger bodies, producing the first building blocks of planets. And in these regions, we have also, there is a star-disk interaction where accretion and also ejection through jets or winds occur. And this star-disk interaction, the accretion shocks, also impact the evolution of the central star and its disk. And this defines the initial and environmental conditions for planet formation. But if we would like to probe these first 10 AUs, we need to have high angular resolution that is reachable with near-infrared interferometry, for instance, with gravity, working in the K-band, and that combines the 4 telescopes of the VLT to synthesize a giant mirror of more than 100 meters in diameter. But the price to be paid is that we have no longer beautiful images, but a beautiful fringe pattern from which we have to extract the use of the relevant observables. But this allows us to reach really the angular resolution that is needed. So a few words about the interferometric observables. The fringe and the contrast or the visibility of the fringes give us access to the extent of the objects. The diameter, but also the sharpness of the environment can be probed with the visibility as plotted as a function of the separation between the telescopes. And the quantities that is called the closer phase give us access to the asymmetry of the environment. And this is really important if we would like to probe the substructures in this inner region. When we couple an interferometer with a spectrometer, which is the case of gravity, we could derive the same quantities, but as a function of the wavelengths or as the function of the velocity. And so here you are, the spectrum could have, for instance, for the hydrogen bracket gamma line, and we could have access to differential visibility to the relative extent in the line with respect to the extent that we measure in the K-band continuum. And we have access also to differential phase, and this differential phase could be translated without modeling assumption on sky displacement. So we can trace the photocenter of the object as a function of the velocity. And this is really important because what you can see here is that we are able to probe size of the order of a few hundredths of AU. So this is really at the scale that we would like to probe to understand what happened in the innermost regions of young star. So we have led a large program with the gravity guarantee time of the consortium. And this is our sample today. So we have about 40 T-Tauri stars, so class 2 low mass star. We have almost 60 Air-big stars, so intermediate mass, and more than 15 high mass YSOs. And our idea is really to use the sensitivity and the accuracy of gravity to lead a statistical approach on a large sample, and also to simultaneously study the K-band continuum, so the dust emission and the hot and warm gas emission using the spectral ability of the instrument. So with this huge sample that is also homogeneous in terms of data set, in terms of modeling, we can look for trends with the properties of the central star and also with the disk morphology. So I have plotted here what we call the radius luminosity relation. So this is the size that we measure with gravity as a function of the stellar luminosity for the T-Tauri stars in green, for the Air-big stars with the triangle, and the color of the triangle codes the morphology of the disk, if the disk is flare or flat, and for the high mass YSO in purple. And what we see is that our measurements are consistent with passively radiative disk with optically thin cavity, and that the peak of the emission in the K-band continuum corresponds to the dust sublimation rim. But we see also some scatter at large luminosity that could be due to accretion of dust warming, of self-shielding. And we have also to take into account light scattering at low luminosity. And the interest of this measurement is that we can use them to test different advanced model of the inner rim as those that are depicted here. We can also use our data to link the inner and the outer part of the disk. And this is an example of a statistical study on 20 disks with known dust-depleted cavities. And we derive the orientation of the inner disk with gravity in the K-band, and we can compare them with the orientation of the outer disk that we could derive using the ALMA-CO map. And for 6 among our 20 targets, we clearly detect an inner-outer disk misalignment, and we can use we can use this misalignment to predict the shadows that are expected within, in this case of misalignment, the shadow that we observed in the sphere image, as you can see here on the right. And the prediction are in blue, coming from our misalignment measurement, and you see that it nicely fits what are really observed on this object. So we use these observations to understand which processes induce such misalignments, and more generally to connect the substructures that are observed at large scale with those that are supposed also to exist at smaller scales. So indeed, the outer disk is known to exhibit lots of substructure, rings, spirals, arms, and in addition to that, they are temporally variable, as you can see here on the Herbig's on this Herbig image coming from sphere, and you see different timescale variability. And so there is a need and also an interest to indirectly map the innermost regions that might be as diverse and as variable as the outer ones. And here you have an example of 2 best model images that has been retrieved from gravity observations for this Herbig star for 2 different epochs. And you clearly see a variable substructures at a very small scales, and that could be either a vortex or a variable shadowing, and so we need to understand and to connect this variability to the large scale variability. I just would like to emphasize the size and the scales that we are able to probe with the gravity measurement, and to be compared with what we can probe with the sphere images. So we are not speaking about the same scales, but we need to connect all these scales together. Another example of the variability that we could probe with gravity is for this Herbig star, for which we have more than 5 years of observations. And when we reconstruct images from our measurement, we clearly see a kind of large vortex at 1.3 AU orbiting around the star. And this kind of substructure at such small scales should be also understood. And we can relate this structure with a vortex or a dust trap or inhomogeneous illumination of this inner rim. For this object, we also have a measurement in the bracket gamma line, and this is what is coded by the color circle here when we measure the photocenter of the emission in the bracket gamma line for this object. And we derive the size of the bracket gamma emitting regions of 0.37 AU, so much compact than the inner rim of the dusty disk. And we can so locate the emission as a function of the velocity. And we can do that for different epochs. And what is really interesting is that it seems that the bracket gamma emitting region seems to remain between the star here in white and the arc we detect in the dusty disk. So either we are passing an asymmetric disk wind or the accretion on a companion. This has to be understood, but it's really interesting. And with that, I will also continue with example of what we can do when using this spectral ability of gravity and observing by interferometry across emission line. And this is a really nice tool to probe the accretion and ejection phenomena in the very innermost region, and to locate the gas emission and its kinematic. So there is also a huge interest to couple this gravity observation with spectroscopic observation to have a accretion ejection proxy across bracket gamma line, but also helium line and so on, and also to couple this observation with spectropolarimetry to have access to the magnetic field topology. This is an example of what we have done on the young nearby T-Tauri star TW Hydra. So we have recorded with gravity the bracket gamma line at a spectral resolution of 4000. And for each spectral channel, we can derive the size of the bracket gamma line. And we obtain an emitting region with a size of 4.5 solar radii. And in parallel, we have also spectropolarimetric observation with the espadon in the visible, and we can derive the topology and the strength of the magnetic field, which allows us to derive the size of the magnetosphere. And we see a nice agreement between the two scales. And so our observations are in nice agreement with the magnetospheric accretion scenario. And to check that, we have developed radiative transfer model of this magnetospheric accretion. And from that, we can derive synthetic observables, synthetic lines, as you can show here for the bracket gamma line, for instance, but also from the images, we can derive the synthetic interferometric observables as it had been done for ALMA and presented previously in the session of this conference. And we do that for TW Hydra, which is a polon object. So here you have an image of the magnetosphere, and we can extract the size corresponding to the model in purple. So this is the cycle, the purple cycle, and sorry, and you see that the superposition is really nice. So we extend this kind of study to a larger range of T-Tauri stars, and here we plot the size of the bracket gamma line we derived with gravity, so in yellow, and we compare them with the co-rotation radius, which is the green cross in this graph. And indeed, if the dominant driver of the bracket gamma emitting regions is magnetospheric accretion, we expect that the bracket gamma line and the co-rotation are at the same order of magnitude. And this is what we observed for the weak accretors as TW Hydra, but we see also some object for which the size of the bracket gamma line is much larger than the co-rotation radius and even larger than 10 stellar radii. So suggesting that magnetospheric accretion for this object is not necessarily the only contribution to the bracket gamma line emission. And there is also an interest to compare the bracket gamma line size with the co-rotation radius, because simulations show that this is a relevant quantity to know whether the accretion is stable or unstable. And you will have a focus on the SCRA results given by Hugo Novaki just after my talk. So since we suspect that the bracket gamma emitting region could be a combination of magnetospheric accretion and ejection, we had in-house simulation in our radiative transfer model. On top of this magnetospheric accretion, we had a conical disk wind. And we use, again, this simulation to produce synthetic interferometric observables. And here on the right, you have a comparison of what we have for the T-Tauri star RU loop with the gravity data in black and the modeling in purple. And again, the line of the bracket gamma line, but also the size across this line are well reproduced by the model. And for this photocenter, we need to understand why there is this discrepancy. So now I would like to say a few words about the future. The future is the upgrade of gravity, the so-called Gravity Plus instrument that will upgrade the adaptive optics of the different telescope. And this is foreseen for the coming weeks, so this summer, and also to install laser guide star on each telescope in 2025, 2026. And this is really important because it will increase both the sensitivity and the sky coverage. So you can see on the left in the color diagram, in the gray zone is the target that are reachable today with gravity, and in the purple one is the sample that will be accessible with Gravity Plus once the laser guide star will be installed. And you can see that we will be able to access different star forming regions with different age. And this is important to study the disk evolution over key timescales for planet formation. So we will be able to have more representative samples by exploring a larger parameter range in mass, in age, in accretion rate. And this will also allow to test the magnetospheric accretion scenario in different regimes. And the increase of sensitivity will also help us to have access to the bulk of the T-Tauri star and to lead the studies across the spectral line in a much more larger sample, as you may show in this histogram here. So we will really be able to probe the bulk of the T-Tauri stars, so to go to fainter target, or we can on brighter target, be able to retrieve the interferometric observables during very short time, and then to follow the accretion flows and to be able to have the time resolution that is needed to really probe the accretion ejection process, and also to connect them to the photometric variability or the variability of the magnetic field, for instance. And so to conclude, I would emphasize a few takeaway messages to the Gravity YSO Large program as providing us with an invaluable homogeneous data set that allow us to start demography studies as those that has been done with HALMA or with SPHERE, for instance, to look for trends with central star properties and to test advanced disk structure and accretion ejection models. And we will also be able to start to have some variability studies and to understand at which time scale the different substructure or accretion flow varies. So there is gravity will provides a unique piece of the puzzle to understand the star forming processes and to have an overview of the protoplanetary disk. And there is a huge interest to combine these observations with James Webb observation, ALMA observation, spectropolarimetry, and in the future with the ELT, and also with the different instruments that are now available at the VLTI to have bridge the gap between the inner and the outer scale of the disk. And I will finish with this illustration of what we have recently done on this big star when we are able to map the disk, which is a multi-ring disk with zones of different compositions, with a radial mineralogy gradient whose origin has to be understood, but for wavelengths between 1.7 micron to among 12 micron. And you see that we are able to probe really different scales. So I will stop here and I will be more than happy to take some questions.
Time for a couple of questions. Please raise your hands. Okay, there is a question in the chat.
I cannot see it. Sorry.
All right, can we check short period variability over a few hours in the K band with Gravity Plus?
Yes, this is really what we would like to do. And we are now able, for object, we are now able to, yes, to compute, for instance, the photocenter at the scale of a few tenths of minute or less, and Hugo will develop that just later, but this is really the aim. But to be really useful, we really need to have simultaneous observation, for instance, with photometry to correlate, and ideally with also spectropolarimetry to be able to correlate all the things together, the structure that we resolved in the innermost region, but also the flux and also the magnetic field variation.
All right, and we have time for one more question. Anybody? Okay, if not, let's thank Karine again. But wait, there's more. The next talk will be by Hugo Nowacki, and I think you are going to be focusing on one of the gravity stars. If I remember correctly, it's SCRA, but I don't have my notes in front of me. Right, so, oh, that's yours now.